Okay, so now, hopefully, you know how a muscle contracts. But let's add some more detail. Let's talk about the phases through that contraction and also how we can have it have various strengths, because it doesn't always contract with the same amount of force. Think about lifting an empty cup of coffee versus a full cup of coffee. If you did it the same every time, you would just splash coffee all over your face. Not ideal. So we have to have a way to control the strength of those contractions. But first, before we get that far, let's make sure we're all on the same page about what's happening during those contractions. So during a muscle contraction, you're increasing the force by shortening the sarcomeres. So the sarcomeres are those repeating functional units along the muscle. So each one shortens along the way, shortening the whole muscle. So you're just pulling. Muscles only pull, they will never push. Now, when you go to do that contraction, there are three main phases or three main events that have to occur for that contraction to take place. So you'll start with the latent period. The latent period is a little bit of time between when the muscle is signaled, so I think of it as kind of once you have acetylcholine bind to the receptor on the motor end plate, all the way until you can actually get the myosin head to pull. That's called a power stroke. So this is from when the muscle is notified, so they know, so signaling, over until you get power stroke. So the last step right before the power stroke is going to be cross bridge formation. Okay, so recap, what does that look like? You have a chemical message released from a neuron over to the motor end plate, which is the part of the muscle that has the receptors. You will then create an electrical signal that will spread across the muscle down the transverse tubules. That will signal the storage area, the sarcoplasmic reticulum, to release calcium ions. Those calcium ions will bind to troponin, which is a part of your thin filament. It causes that troponin to change its shape, and when it does that, it will push a blocking molecule called tropomyosin out of the way of the binding site for these little heads. And so what you'll end up having are these binding sites now exposed. Myosin heads can grab them. That's the cross bridge. Now, once you pull, this little arrow here is the difference between latent period, and I guess I probably shouldn't have it there. I'm going to move it over. So we're going to have this part be the cross bridge. So now we're touching the thin filament, which is actually circular. And so we're going to have cross bridge formation. And then as soon as you get the pull, as soon as you get that power stroke, you now have a contraction. So that's now the contraction phase. Contraction phase actually is just a bunch of these repeated. So you're doing what we call cross-bridge cycling. You're going to take turns with the different heads, pulling, pulling, pulling. So think of it kind of like tug of war team on a rope, pulling, pulling, pulling to shorten that sarcomere. And then you'll have the relaxation phase, which is when your tension returns back to normal. So if you're going to kind of look at these three, here you have no tension, no tension, no tension. Here you go up to a peak, here it falls back down. So with the relaxation phase, some of the things you're going to be doing would be like putting the calcium back into their storage, which was the SR, sarcoplasmic reticulum. And so here, you're going to actually use up a lot of ATP to put things back into storage and to reset the myosin heads. It takes energy to get that to go back. And so we're going to reset. And that's going to use ATP to do it. All right, so those are your three main events along a muscle contraction. So if those three main events always kind of happen the same way, how do we get the muscle as a whole to contract with different forces? It's a couple cool tricks. One, just use more cells. When you look at a muscle, you actually don't activate all of the fibers at once. You can pick and choose the groupings of them that you want to use. So our first idea is get some help. So option one is going to be recruitment. This is when you're going to activate more motor units. So recruitment is basically turn on more of the motor units, and that gets you more cells, and the more workers you have involved in the problem, the more power you can create. Another thing that you can do is going to be signaling based. So another thing that we can do, number two, is increase the frequency of signaling. So increase action potential frequency, shorthand. Now, when you send a signal, you can give it time to reset fully, and it would fall all the way back to its normal resting point. Or you can send your next signal sooner, in sooner. And if you haven't gotten all the calcium up, you have a buildup of calcium, and you have more calcium available each time. And so you can actually make this contraction generate with more force. So let's take a look at what that would look like. So let's say you're signaling at a base level, and so you can kind of come back, you let it rest, it'll come back, you let it rest, it'll come back, you let it rest. But you could, if you get them close enough together, come back and build them if you start setting one right after the other, because you're also warming up the muscle. So molecules move faster when they're warmer. This is a warm-up effect. And so even if you let it fully relax, those molecules, when you do let them out, will be able to move a little bit more efficiently. You could also signal to contract before you even let it reach all the way back to rest. Eventually, you'll max out, and you could even flatline it a little bit. Now, not in real life. You actually have to do that with some experimental stuff. Real neurons can't talk at the speed to let it lock out like this, but you can do this, where it kind of like fluctuates a little, and then it goes back, and it fluctuates a little, go back. And each of those have different names. So the first one up here is TREP. And then, oh, sorry, this one's slow. TREP's not till here. Should have noticed that. So TREP, they build. Here is just low frequency. So here, you don't have any building. TREP, you're building. Here, you're not letting it come all the way back to rest. This is wave summation. And here is tetanus, or tetany. So a couple of cool tricks for how to work with all of this. So if you go through each one of these, there's really three main things to keep track of. The first one is if it starts to relax. So if you let it even start kind of going back down that hill. The next thing you gotta ask is, does it fully relax? And then the last thing you have to ask is, does tension increase? So increase force. So let's go through each one of those. So let's do the low frequency one first. So low frequency, this part right here. Does it start to relax? Yeah. Does it fully relax? Yeah. Do we get an increase in force? No, they all stay the same. But if we go to tetany, no, let's not go to tetany, let's go in order. That would make way more sense. If we go to TREP, it will start to relax, yeah. It will fully relax, yep. But it doesn't stay there for long, and then in the next one, it actually builds. So you get an increase in force. That's the difference between here and here. Now we're starting to build. Now your next one, wave summation, I'm gonna shorthand that. So wave summation, do we start to relax? Yeah. Do we come all the way back? No. So we don't fully relax. And do we build with each one? Yeah. So there's your difference there. Well, yes, you're building. The difference here is you don't let it get all the way back to your baseline strength. And then your last one, tetany, do you start to relax? Yes. Do you fully relax? No. Do any of these get any higher? No. You're maxing out on each one. So there's your best way to organize that. I actually think that's pretty helpful to kind of see it all on a table. Okay, so that's increasing your frequency. So you can get more cells, you can increase your frequency. And the third option is based on where you position to start with. And so this one is going to be based on sarcomere length. Remember, the sarcomeres are the functional units which you're going to be pulling on. And there is an ideal length that you want to be at where you can generate the most tension. And so you can position yourself in a way to get there. And we do it naturally. Like, think about it. If somebody says, jump as high as you can, what's your first move? Like, just try it right now. Like, hit pause, jump as high as you can. Okay. If you're told to jump as high as you can, your first move is actually to go down. Which is weird because, right, you want to go up. The goal is up. Why go backwards? Why make it further that you have to go? Because what you're doing is you're going to, when you squat down a little bit, is you're going to put your muscles in what's called optimal length. So with your sarcomere, if we remember our anatomy here, it's going to have the Z lines. And then you have in between is your thick filament. And on your thick filament are the heads that you want to be able to reach up and grab a hold of the thin filament. And if you have your muscle set up where it's stretched out or elongated too much, you won't have as much overlap. So could you imagine if I were then to put it first at optimal length? Let's do that. So let's say all of the myosin heads have the ability to grab onto a thin filament. So they can all grab a thin filament and they can all pull as soon as it's time, and they have a ton of room to work. But what if I took these and moved them over? And now, let's say we do that real quick. So we shorten that up, so slide this over. It's not easy to do, but we'll just pretend. So what happens if I slide this over is that you're going to end up having some of the myosin heads that can't reach anything. So if we're too stretched out, you're not going to be able to reach all the myosin heads to a part of the rope. So think of it as a tug-of-war team that's now going to have some people in the back going, okay, I can't grab anything, I have to wait till you hand me the rope. You don't get to generate as much tension. The other problem would be true is if we compress it. So if we were to say on this side, show it the other way, where I bring it in, and then I pull some of my rope over this way. When you give your tug-of-war team the green light and say, okay, everybody pull, and then they're like, I can't go any further, they're not going to generate as much force because they run into the Z-line too soon. And so that's where the idea of the optimal length comes in. So optimal length is where you can first get all of the myosin heads to have something to grab a hold of once it's time to create tension, but they have longer to go until they run into the Z-line. So if you're stretched, not all the myosin heads can reach. If you're compressed, you run out of space before you can actually do enough contractions to generate as much force. So those are your three main options. We can get more fibers, we can talk to it faster, or we can make sure that the sarcomere is set in a position to give us the strongest contraction possible. So those are different ways that we can create more tension with the muscles that we have. And then, there's also the idea of train the muscles, get some more proteins, but that's a whole other talk. All right, thanks for watching.